So in HR analytics file, the dependent variable is underscore promoted. The dependent variable is underscore promoted is a dependent variable. Whether the employee is recommended for promotion or not. 0 means no, 1 means yes. Employee being recommended for promotion. So 50,000 employees were not recommended for promotion. 4,668 employees are recommended for promotion. Here the dependent variable is what? Non-numerical and binary. Here the dependent variable is non-numerical and binary. So HR analytics. Okay, HR analytics 10, all of you have opened it. Okay, all of you open it and run all the cells. Test null, the average underscore training underscore score of is underscore promoted 0 and 1 equal. Test null, the average training underscore of is underscore promoted 0 and 1 is equal. Now there are exactly 2 levels in is underscore promoted. So this is a classic case for 2 sample independent t-test. Exactly 2 levels are there, 0 and 1. So let us first find out what was the HR train dot df dot average training score dot group by HR train df dot is underscore promoted dot mean. The means are different. Employees who are not promoted, their average training score is 62.64. Employees who are promoted, the average training score is 71.32. Got it, all of you? The HR analytics file, just run all the cells. We have done the pre-processing and all those things in this, right? Anybody needs the file or all of you have the file? You check your email, it will be there. So there is a mean difference. Since there are exactly 2 levels in categorical variable, what we can do? We can do the hypothesis test, 2 sample independent t-test. We can do 2 sample independent t-test. Because why we are using the word independent here? An employee will be promoted or not promoted. He cannot be both, right? An employee will be either promoted or not promoted. He cannot be both. That is why we call it as independent sample. So, two sample independent t-test. The null hypothesis is there is no significant difference in average underscore training underscore score of is underscore promoted 0 and 1. There is no significant difference. No significant difference means that means you can treat them equally. Then copy paste the statement null to alternate and remove the word no before. It becomes a significant difference. Okay. Now we have to split the data. Promoted S is equal to HR trained DF square bracket HR trained DF dot is promoted double equals to 1. Promoted no is equal to HR trained DF square bracket HR trained DF dot is underscore promoted double equals to 0. Okay, all of you got it? Now we will conduct the test after importing the function. The function is from scipy dot stats import t-test underscore ind. T-test underscore in promoted yes dot average training score comma promoted no dot average training score, comma, equal underscore var is equal to false. So we got the p-value as less than 0.05. Will get the null. Audit t-test, two sample independent t-test when we have exactly two levels in the categorical variable. Is underscore promoted has exactly two levels, 0 and 1. 0 represents no, 1 represents yes. In binary distribution, in binary variables, 0 by default is always no, 1 is always yes, alphabetical order. Why? Because it is alphabetical order. Until unless specified, treat 0 as no, 1 is always yes. That is the standard in data science, until unless specified. Unless it is specified as the other way around, you will treat it as 0 as no, 1 as alphabetical order. Test null, the average length underscore of underscore service of is underscore promoted 0 and 1 equal. So the data is already split. Write the null and alternate. First, do the group by. First, do the group by of mean and also group by of variance. Do the group by of mean and also group by of variance. Because we have to make sure the variance is also different. And then frame the null and alternate. Then conduct the test. 5.87 and 5.71. Variance is also different, right? Equal underscore var is equal to true. You have to give equal underscore var is equal to true. That's it. Assuming equal variances, what happens is, if the denominator square root of variance, right, both variances are same, then it will create problem, right? There has to be variance difference. Otherwise, equal variances, there is another formula. Null is no significant difference in average length underscore of underscore service per is underscore promoted 0 and 1. Same statement, copy and paste. Null as alternate and remove the word no. Significant difference. T-test underscore int promoted yes dot length of service comma promoted no dot length of service comma equal underscore var is equal to false. So p value is less than 0.05. So we will reject the very marginal difference, right? The difference is very, very small, but that is also a very big difference. That is a significant difference. See, 5.8 and 5.7, sorry, 5.71 and 5.82. Yeah, 87. Only the difference is 0.16. But still, it is a significant difference. But still, it is a significant difference as per the hypothesis testing. That means we cannot treat the differences equally. Yes, please.
So for t-test, just for IMD documentation, like for independent two-sample test, we assume equal value is true.
Yeah.
And for Welch's t-test, we assume it is false.
Yes. So Welch we are doing Welch two-sample t-test. Welch two-sample t-test is the independent test with assuming unequal variances. Welch two-sample t-test is the test for assuming unequal variances. If you look at yesterday's, in the last session Excel also, we have two different. See, assuming equal variances, assuming unequal variances. Unequal variances is a Welch two-sample t-test. Assuming equal variances is your normal t-test. So you have two options here: equal variance and unequal variance. The formula is different, right? In Excel also we have. See, paid is your normal before and after. Paid t-test is before and after. The other two t-tests are assuming equal variances, assuming unequal variances. Equal variances is a very, very hypothetical situation, which will happen in weather data or economic data, like GDP or something. It happens mostly in weather data. When you have long-term days of same climate, take for example Iceland, Greenland, those countries, in 365 days for 200 days they don't have sun. Their climate is always somewhere between 0 degrees to 4 degrees or -4 degrees. So it will be very, very small variance they have when you don't have sun for days together. So the variance will not be there. If there is no sun, there is no temperature. If there is no temperature, the variation will not be there. So there you have an equal variance situation. When there is no change, if it is a straight line thing, the equal variance will be equal, right? So that happens for some temperature scenarios like Greenland, Iceland, European countries where for days together they don't have sun. In a year, they get hardly 100 days or less than 100 days sun only. So their temperatures will be stagnant. Every day similar temperature. So obviously there the variance will be less. That is what happens. Similarly, if in a hotel will constantly maintaining 24 degrees temperature in a star hotel. The daily temperature will be that only, right? Average temperature will be around 24 only. Hotels, 5-star hotels and all, when you do the sensor-based calculations, you'll get a constant temperature maintenance. They maintain it constantly, software parks and all. Until somebody changes the temperature, it's a constant one. So when it's a constant, will there be variance? There will be no variance. That is what you have to understand. Okay, so X null, the average underscore training underscore score for different recruitment channel. Recruitment underscore channel is equal. First do the group by, find out how many levels are there, then do the splitting, then do the null and alternate, and then do the test. Chart trained here, average training score, not group by, chart trained here, dot recruitment channel, dot mean. So how many are there? 3 are there. So what test we have to run? On our single factor. Uh, uh, which DF part is in? Uh. No, DF will be in the bottom. In the beginning, it will be HR train only. In the last, we have done the train DF after doing the pre-processing. We have converted into DF. After combining and pre-processing, in the last, you will see the DF. Most of it is train only. Here, from cell number 82 onwards, we see the DF, where we split the cleaned data into train and test back. Earlier, we combined them for cleaning. Now we are splitting them back. Now HR train 0, 1, 2, 3, what does they mean? 1 second. We have done the recruitment channel thing, right? Earlier, group by. DF is a short form for data frame. Recruitment channel, other referred sourcing. Let me just run the name so that it can be confirmed. Number of things. Other referred and sourcing. 0 is other, 1 is referred, 3 is sourcing. Okay. Other is equal to HR train DF square bracket HR train DF dot recruitment channel double equals to 0. Referred is equal to HR train DF square bracket HR train DF dot recruitment channel double equals to 1. Source is equal to HR train DF square bracket HR train DF dot recruitment channel double equals to 2. So other is 0, reference is 1, sourcing is 2. So what is the function? F underscore one way. From SciPy dot stats import F underscore one way. Now you can do the test. F underscore one way, other dot average training score, comma, refer dot average training score. So what is your analysis? Reject null. F underscore one way, other dot average training score, comma, refer dot average training score, comma, source dot average training score. P value is less than 0.05. Reject null. One more test, test null average length of service. Of different recruitment channels. Equal. 5.89, 4.97, 5.87. F underscore one way. Other dot length of service, comma, refer dot length of service, comma, row dot length of service. Reject null hypothesis, right? Right? For analysis of variance, no required. For ANOVA, it's not required. Only for t-test independent, the t-test only you have to do it. That too for independent sample, not for paired sample. Axis, if your data is in row, columns, our data is in rows, right? When your data frame is in reverse, that means observations are in columns, variables are in rows. Then you have to use axis is equal to 1. It happens with some old databases. That even before that, we will transpose the transpose. You can do the transpose, right? So we transpose the data and we run it. The best way is always running the observations on rows, variables on columns. Sometimes in old versions of database, you have the reverse, where your observations will be in columns, variables will be in rows. Even that table also we transpose it. Dot T is there. Transpose is very easy, right? It automatically does it and then you can do it. So that axis is equal to 1 is a very rare scenario. But we avoid doing it by transposing the data frame. By converting rows to columns, columns to rows. That is the best option. Okay, now let us do some chi-square test. Test null, no association between gender and is underscore promoted. Test null, no association. So chi-square test is cross tabulation. First you have to do cross tabulation, then you have to do chi2 underscore contingency. The function name is chi2 underscore contingency. Reject or failed reject? Reject. So PD dot cross tab HR train DF dot is underscore promoted, comma, HR trained df dot gender cross tabulation from scipy.stats import I2 underscore contingency. I2 underscore contingency is a cross tabulation. So P value is this. Okay. Hmm. Hmm. There is a relationship. Same thing. In the interpretation is the difference in means is significant. It means you cannot treat them equally. This is a significant variable you have to include in your model building. See, whatever hypothesis test says reject null, those variables are significant and you must include them in your model building. That is the ultimate final interpretation. Whichever variable is found significant in hypothesis testing by rejecting the null hypothesis, those variables have an effect with the dependent variable. So you must include them in your model building, like in regression. So suppose you are deciding you have too many variables. You can't do all hypothesis tests, you can't do on all variables and also you randomly choose some variables which you think are logically important, run the test. If they say reject null hypothesis, you have to include them. So the premise is if the hypothesis testing says reject null, that means the difference in means is significant. Now you have to study what is causing the difference in means. How will you study? Using a machine learning model. Using machine learning models, we will study why there is a variance in the data or why there is a change in a trend or a pattern. So hypothesis testing will simply validate that there is a change. You cannot treat them equally. Now, if you cannot treat them equally, what is the cause in that? How will you study? Using a machine learning model. That is what the relationship between hypothesis testing and machine learning. Machine learning models will help you to understand what are the reasons or what are the variables that are having this change in pattern, where we found that the rejection of the hypothesis, null hypothesis, done. Rejection of null hypothesis means the difference in means is there. Now, what is causing this difference in means? Other variables or the dependent variable? How will you study? Using a model, regression model or a classification model. Okay. Now, let us get into the second type of our supervised learning. Within supervised learning, yesterday we studied the regression algorithm, multiple linear regression. Today we will study the fundamental classification algorithm called binary logistic regression. So we will today study the fundamental classification algorithm called binary logistic regression. Yesterday we have studied the fundamental regression algorithm, multiple linear regression. Binary logistic regression explains the linear relationship between a binary dependent variable, a non-numeric binary dependent variable denoted by y that has exactly two levels or groups like yes or no and multiple independent variables. Binary dependent variable and multiple independent variables. The equation is P is equal to e to the power of, e is what? Exponential. Exponential to the power of b0 plus b1 x1 plus b2 x2 plus b3 x3 plus b4 x4 till bn xn, e to the power of. The denominator will be 1 plus, say, 1 plus e to the power of. This is the equation of binary logistic regression. Binary logistic regression explains the linear relationship between a non-numeric binary dependent variable that has exactly two levels, yes or no, and multiple independent variables. The equation is P. P represents probability. P represents probability. And probability lies between 0 and 1. Probability. P is probability. In regression, you get predicted value. Here you will get predicted probability. And the probability lies between 0 and 1. So, what is P? P is probability. That lies between 0 and 1. exp is nothing but exponential. What is the value of exponential? 2.718 power of, right? Then b0 is again intercept or constant. Then b1, b2, b3, b4 till bn, we call them as coefficients, are slopes x1, x2, x3, x4 till xn, we call them as independent variables. So this is the equation. we get predicted probability. Here also we have to solve for the coefficients and the intercept. We have the values of x, we have values of y. We have to solve for the coefficients and intercept. Same how we did it in regression. Here also we have to solve for the intercept and coefficients using log loss function and a solver. Minimization, linear programming, minimization of the error is what we have to do. Assumptions. The assumptions are dependent variable y must be non-numeric and binary. It must be either in the form of yes or no, or true or false. Either in yes or no, or true or false. Independent variables can be both numerical. Independent variables can be both numerical and non-numerical. Can be both numerical and non-numerical. Independent variables. Third, no multicollinearity. There should not be multicollinearity among variables. If found, do not include both. Choose one among them. Fourth, sample size is minimum 50 observations per variable. Sample size is minimum 50 observations per variable. There must be a logical linear relationship between dependent and independent variables. These are the assumptions which you need to understand for binary logistic regression. Okay. Now, the classification rule. The classification rule. So, in classification, we get the probability. Probability greater than equal to 0.50 classified as 1. Probability less than 0.50 classified as 0. This is the classification rule which is implemented across classification algorithm. Once you solve the equation, you will get the predicted probability. Based on the predicted probability, you will classify. If the probability is greater than equal to 0.50, it will be classified as 1. If the probability is less than 0.50, it will be classified as 0. Okay. The interpretation of output. The interpretation of output in Python is based on confusion matrix. The interpretation of output in Python is based on confusion matrix. Confusion matrix is a 2 by 2 matrix for binary dependent variable between actual class and predicted class. Actual class or level, predicted class or level. So confusion matrix is a 2 by 2 matrix. Now this confusion matrix is a very important tool for our analysis. So let me show you the confusion matrix. So this is the confusion matrix. Okay, so you have 4 quadrants. The first quadrant is actual class is positive and predicted class is also positive. Predicted class is also positive. Actual class is positive, predicted class is positive. We call this as true positive. Now, actual class is negative and predicted class is, sorry, actual class is positive and predicted class is negative, which is wrong classification. We call it as false negative. Similarly, actual class is negative and predicted class is positive. Call this as false positive. Actual class is negative and predicted class is negative. We call this as true negative. So confusion matrix is very critical, which is a 2 by 2 matrix of the actual class and the predicted class. The actual class is a 2 by 2 matrix. 4 quadrants will be there in a 2 by 2 matrix. Okay. So this is the confusion matrix. The four quadrants of the confusion matrix and various formulas which are needed. The primary metric is accuracy. The primary metric is accuracy. Accuracy is the primary metric. The formula for accuracy is true positive plus true negative, correct predictions by all predictions. True positive plus false negative plus false positive plus true negative. The primary metric for all classification problems is accuracy. The primary metric, like R square is the primary metric for all regression problems. Here it is accuracy for all classification problems. The primary metric for regression problems is R square. Here the primary metric is accuracy. Then we have certain other metrics which are also important in some situations, like sensitivity, also called as recall, sensitivity or recall, which is true positive divided by true positive plus false negative. True positive by true positive plus false negative. This is the formula for sensitivity. Specificity is another problem, formula which we are interested. Specificity is equal to true negative divided by true negative plus false positive. True negative plus false positive. Then we have one more formula called precision. Precision is true positive by true positive plus false positive. And then we also have one more formula which is nowadays considered very important, which is the F1 score. F1 score is equal to 2 into precision into recall. One second, let me check. Two into precision into recall divided by precision plus recall. Precision plus recall. So these are the various formulas which are there in confusion matrix, but the primary metric is accuracy. So in Python, we get accuracy. We get accuracy, then we get the intercept and the coefficients. Okay. So this is the confusion matrix, which is very important in classification problems. HR trained here dot columns. What variables we have. Okay. So y is equal to HR trained here dot is underscore promoted. X is equal to HR trained here dot drop square bracket employee ID. You don't need employee ID, comma is underscore promoted, comma axis is equal to 1 is column dropping. We are separating the data into dependent variable y and independent variable x. In x, we don't want employee ID because there are 54,000 unique values. Your model will never fit. That's why we are removing employee IDs. Then is underscore promoted is the dependent variable which we have already separated. So we are dropping it from x. Y is your dependent variable, x is your independent variables. In independent variables, we are dropping two columns. One is the dependent variable column because one column cannot be in two data frames. So that's why we are dropping them. And the employee ID, 54 unique IDs, 54,000 unique IDs will be there. That's why we are dropping them. So y is equal to le dot fit underscore transform. We are label encoding y. Label encode dependent variable. Because we have not encoded it, right? In the last session, we didn't encode the dependent variable. So we are label encoding the dependent variable. From sklearn dot linear underscore model import logistic regression. Logic is equal to logistic regression. Logic model is equal to logic dot fit x comma y. Oh, it says model could not be built as total number of iterations have reached the limit. So we'll increase the iterations. F underscore iter. Logic model dot score x, comma y. This is the accuracy from confusion matrix. This is the accuracy from confusion matrix. So the algorithm will build a confusion matrix in the backend and it will give you the accuracy. The score function here will give you the accuracy, which is calculated by creating a confusion matrix in the backend. Now, if you want to see the confusion matrix, you can also see it by printing it. Logic predict is equal to logic model dot predict of x. PD dot cross tab y comma logic predict. You can see the confusion matrix. Hello. Okay, I'll send them today. Yeah, I teach complete machine learning, including deep learning. Yeah. Okay. Now calculate the accuracy. Horizontal are correct predictions, no? Sorry, diagonal. The diagonals are correct predictions. Rest of all are wrong predictions. So if you can check here, 49,948 plus 325 divided by all. 49,948 plus 192 plus 4343 plus 325. You'll get the same 91.72 what you got in the top. See, to the decimal, you'll get the same value. Got the same value, right? So you can see here, this value and the top 91.72 is the same value. So how diagonal are correct predictions. 49,948 is the correct prediction. 325 is correct predictions. The other two are wrong predictions. TP plus TN by TP plus FN plus FP plus TN. You got different, huh? She got different, huh? Accuracy is same, right? Only the changes in there, because there is random selection in the function. In logistic regression, there is something called randomized state. So some of you, we have not fixed the randomness, so it will be there. So if you look at the logistic function, just check the function. You will see there is some randomness, random state also is there. Logistic regression, scalar. This is the function arguments you can see here. Here you can see here random state. If all us give random state as same, like random underscore state is equal to 4, 2, we set a seed 4, 2, then all of us will get the same output. Otherwise, all of us will get slightly different output, but overall it will be same. So you can see here a lot of arguments are there. We generally keep them as it is. The primary argument which I have changed is the iterations. Maximum iteration by default is 100. So when I ran the model, I got a warning, right, saying that the iterations are not enough for building the model. So when I ran the model initially, I got a very big error. See, it says, you can see here, convergence warning. Whenever you see convergence warning in machine learning, it means all the coefficients are not calculated. You know the betas, right? For all the variables, if the coefficients are not calculated, then we get this convergence warning. Convergence warning means all the coefficients for the variables could not be calculated. Why it could not calculate it? Because LBFGS is a solver that failed to converge. Why it failed to converge? Because maximum number of iterations have been reached. So what we have to do immediately when you read this error, it is suggesting, see, the solution is also given here. Increase the number of iterations or scale the data. Scaling, we'll talk about it later. Do you remember standard scaler, we talked about it. Scaling data means you have to go back again and do everything and all. Instead of that, increasing iterations is the easy solutions. So I have increased the iterations, which are by default how much? 100. Max iter, I made it to 2000, a random number which I took. I think 1000 also is enough, just a random number I took. It will not affect, but now all the things are calculated properly. So whenever you are doing these classification problems or regression problems, whenever you see this convergence warning, the thing you have to do is you have to increase the iterations. Whenever you see this something called convergence warning, that means the iterations are not enough for the coefficients to be calculated. So if you say 2000 iterations also you get error, you can go up to 3000, 5000. In some data sets, we give 10,000 iterations also. Got it? So you have to read the error. Okay, I would suggest read the error. The error also has the solution. The error also has the solution. And implement the same solution. Like in this case, increase the number of iterations. So just go and increase it from 100 to 1000 or 2000, your choice. If 1000 works, go ahead, keep it as 1000. If 1000 also doesn't work, increase it to 2000. So it's trial and error based. Okay. Now for looking at other metrics, from sklearn.metrics, import classification report. Print classification report of y, logit predict. Now, what do you observe with the classification report? See, the predictions of promotions is very bad, right? The prediction of the algorithm is making predictions of not promoted okay, 92%, 100%, and 96%. But for the promoted employees, is predicting it's very bad. Why? Because we have very small sample of people who got promoted, right? Since we have very small sample of people who got promoted, the algorithm is not able to predict the promoted guys correctly. This problem, we call it as imbalanced data. This problem, we call it as imbalanced data. Now, in the future sessions, once our models are all built, we will talk about imbalanced data. Now, when you have this imbalanced data, you have to balance it. Balancing means you make 50,140 equal to 468 by deleting some data, or you have to increase 4668 to 50,000 by copying and pasting some random rows of data. Or you can create synthetic data and add it to the smaller class, which is the 4668 class. So these type of call it as undersampling and oversampling. We have to use the techniques. The problem here is overall accuracy is good. The accuracy must be between 0.70 to 0.95. In fact, all the metrics in this case, all the metrics must be in range of 0.70 to 0.95. Anything less than 0.70 underfitting, anything above 0.95, it will be overfitting. So 0.70 to 0.95 is the preferred range of all the classification metrics. And all of them must be closer to one another. In this case, we are seeing the class 1 minority class. Class 1 is called minority class. Why we are calling it as a minority class? Because the number of observations are very small. The majority class is 0, where we have 50,140 observations. The minority class is 1, where we have only 4,668 observations. The algorithm is predicting minority class very badly. The algorithm is predicting minority class very, very badly. Look at it, very bad. 0.1 is a very bad, right? 1%, 7%. See, recall. What is recall? Sensitivity. Sensitivity is very bad, 0.07. And even see F1 score, precision into recall, 2 into precision into recall divided by precision plus recall, 0.13. Even precision is 0.63. So all three metrics for the minority class is being predicted worst. So we have to balance the data and then we have to rebuild our model and hope the balanced data will predict the promoted guys correctly. So in classification, we have this problem. Like in regression, we have the problem of skewness, right? In regression, we have the problem of skewness, dependent variable being highly skewed with outliers and all, right? Here in classification problem, we have the imbalance. In regression, it is skewness and outliers. In classification, it is imbalance. Imbalance means one class has too many observations, the other class has too few observations. In this case, 0 has 50,140, 1 has only 4,668. That is why the algorithm is not able to predict the smaller class or the minority class. So in future, we will talk about imbalanced techniques, how we have to rectify this problem. Once we complete all our algorithms, we will get into that imbalanced data. Maybe end of this month or next month, we will be doing the imbalanced data session. And 4-hour sessions on how to balance, and then we will check for each algorithm, how the balanced work and all, we will do that. Got it? So this is the classification theory and binary logistic regression. And the binary logistic is an S-shaped curve. Binary logistic regression is a S-shaped curve. What is the shape of curve in multiple linear regression? What is the preferred shape of curve in linear regression? Yeah, that is straight line is okay. I'm talking about the curve. Curve is bell curve, no? Normal distribution. For regression, we look for what? Normal distribution, right? The bell curve. So here it is S distribution. If you plot all of them into one, the distribution looks like this. I'm talking about the distribution, S-shaped curve. you're talking about the linear relationship, which is a straight line relationship. Okay. So normal distribution is regression. Binary distribution is for classification. And then we will go through these distributions later, but for you guys, distributions are not much important, but you guys, distribution has to be studied. Remember T distribution, F distribution, chi distribution, Poisson, exponential. They all have to be, you guys, statistics guys have to have basic understanding. Cumulative probability distribution, all those things you might have studied, right, in your stats. Thing. So you need to understand some basics of those distributions. But other guys, distributions are not important. They will not ask you in your interviews. For you guys, even confidence level also important. How is calculated? What is the inference of 95% upper level limit and lower limit? Did you do the calculations in your BSc stats, that are confidence level calculations and all? So as a practice, we will do one.